Hello, this is Professor Keen. We have begun discussing Chapter 5 of A Student's Guide to the Great Physics texts, where Galileo is talking about the relationship between pendular motion and harmony. We left off last time by talking about some elementary music theory, and so let me remind you where we were at. Galileo had introduced a way of studying the relationship between musical notes of different frequencies, or of different pitches. And the way one could do this is by using what's called a monochord. So this is, like I said, a very boring musical instrument because it has a single chord. And how one constructs it is by taking a wooden board, putting a couple of bridges on it right here, making perhaps a pulley that sticks out the side, and then stretching a string, attaching a string here, having it stretch over top these two, over the pulley, and then being attached to a weight that one hangs right here. That's the weight. Okay, and then you can pluck this and a musical note will be sounded. And one finds that the musical note can be changed by changing various features of this monochord. One thing one could change is the length right here. So if I measure the length of this string, and if I would find that if I change the length by, for example, sliding this bridge this way or that, or maybe taking another bridge and placing it over the top and plucking one side as opposed to the other, I can change the effective length of the string, and that will cause a different note to sound. So in order to, let me just write that down to start with. So in order to increase the pitch of the note, P-I-T, pitch, by 1 octave, one can, this is the first way to do it, one can have the length of the monochord. That is, start with a certain length and take it to 1/2 the length. Okay, but there's another way to change the pitch by an octave, and so let's think about this. This weight is producing some tension in the string. Let's call this orange T right here. So there's some tension pulling on it, and if you make the weight larger, you're increasing the tension. So one finds that by increasing the weight, one can also increase the pitch, okay? But you have to quadruple the tension. Okay, so take the tension and have it go to 4 times the original tension. That would also increase the pitch by 1 octave. And as Galileo notes, there is a third way to increase the pitch by 1 octave, and that is by changing the type of string, specifically the mass per unit length of the string. Let's call mu the mass per length. I think he refers to this as the size of the string, but you need to distinguish this from the length. Okay, so let's just talk about this as the mass per unit length. You can increase the mass per unit length by using, let's say, a thicker chord. A thicker chord has a larger mass per unit length, and by doing that, you can change the pitch. Or you could use the same diameter chord but make it of a different material. So you could use like the gut string of a horse or something and then change that to a golden wire, and that would change the mass per unit length, and that would in turn change the pitch. Okay, and one would find that one would have to take, I don't know, 1/4 the mass per unit length. So take the mass per unit length to 1/4 the original mass per unit length, and that would increase the note by 1 octave. Okay, so there are 3 different ways in order that one can change the pitch by 1 octave. So this raises the question, I think this is Sagredo who brings this up, why do we associate within music theory the octave with the 2-to-1 ratio, or 1-to-2, depending on which order you want to put it in. After all, it seems to be giving preference to the change in length. So you take the length to 1/2, that's how you make an octave. But why don't we associate the octave with a 1-to-4 or 4-to-1, since you have to quadruple the tension? Or 1-to-4 or 4-to-1 because you have to take 1/4 the mass per unit length to change it by an octave. Okay, so that's the question that's being raised here. So why not a 4-to-1 ratio? Okay, why not associate 4 with an octave? This is right around page 62 that the guys are discussing this. Okay. Now, how do we answer this question? How does Salviati address this question? Well, you might remember in the last lecture a particular experiment we mentioned where one rubs the rim of a wine glass. And when you rub the rim of a wine glass, you will notice that there are ripples on the surface of the wine glass when a particular pitch note is being emitted. And here's the important point. Suddenly, while moving your finger around on the wine glass at the same speed as you're going around and you're making this note and observing the ripples on the surface of the wine glass, sometimes suddenly the pitch will jump up by an octave. And when that happens, the ripples become closer together. Their distance between them is halved. Okay? And that provides a clue for understanding this. So let me give you an answer right now, and then I'll give you a couple of more examples of ways to think about this that will clarify it. And here's the main point that Salviati is making. He says that the pitch of a note, I'll just say a musical note, is associated with the frequency of vibration. You probably have heard this before, but it's not entirely obvious at first. With the frequency of vibration of the instrument string. Okay, so how do we know this? After all, it's not like when you strike a guitar, you can actually see the string and you count. I mean, you can see the string, but it's hard to count the frequency. So how do we know that the pitch is associated with the frequency of the string? So the question is, how do we know? And an example that Galileo provides is related to the vibrating glass. But he says, suppose you were to take a chisel. And he's done this. He says you take a chisel and you scrape it across a piece of metal. So you take this chisel and you scrape it across a piece of metal. I'll try to draw a chisel like this. And you push it. So here's the handle of this chisel. And you scrape it across a surface of metal. And when you do that, it makes a high-pitched screeching noise, right? And sometimes when you're moving this chisel with a certain speed, a certain velocity, and there's a certain pitch of note that's coming out, suddenly sometimes while moving it at the same speed, the pitch will go up, get much higher. And when it does so, you will notice if you take a microscope and look at this, the little marks that are on here are separated by half the distance. So if you were to take a magnifying glass and inspect the little bumps that are being formed by the chisel, so here's your magnifying glass, and you look at these little marks. After all, why is this making a noise? It's because this chisel is skipping across the metal and making little gouges in the metal. And the frequency with which it makes these gouges is related to the separation of the gouges. Okay, so the sound that is made, that is emitted, you might say, is determined by the frequency, how often, the frequency with which the chalk, or I'm sorry, with which the chisel strikes the metal. And we know this because when the pitch goes up, even if you're moving this at the same speed, these little chisel marks are closer together. In other words, it's striking them more frequently, closer together, and the pitch goes up. So somehow the frequency is related to the sound pitch. Okay, and this is a clue to what he's talking about. As another example, I mean, we could do this in the classroom. I could take a piece of chalk and I could move it down the chalkboard with a certain velocity. And when we do this, we will see that the chalk makes these little marks on the chalkboard as it skips across the chalkboard. Okay, and if I were to scrape the chalk down at a certain speed, I could measure the distance between these. Okay, and sometimes you'll notice that there's a much higher pitch, and when there's a higher pitch, even if I'm moving the chalk at the same speed, these separation between these is going to be smaller. Okay, so in other words, the frequency with which these strikes are made is related to the pitch. So the higher pitch corresponds to closer marks. And in particular, we can notice that when two notes are separated by an octave, this might be hard to do, but two notes are separated by an octave, the distance between them is half as long. So the frequency of the strikes is twice as high. The frequency of strikes of the chalk against the board twice as high. That's the point. And this is exactly what Galileo is pointing out on page 64. He states, I'm just going to say this first and I'll go back and write it down. He asserts that the ratio of a musical interval, think about an octave, the ratio of a musical interval is not immediately determined by either the length of this string over here, or by the tension, or by the mass per unit length. Rather, the most fundamental thing that determines a pitch is the frequency of vibration. And the frequency of vibration can be changed by changing any of these three things. Okay, so the ratio of a musical interval, like an octave, the ratio of a musical interval is not, I'm going to get rid of this, put it over here, and I'll put these over here also to give myself a little bit more room, is not immediately determined by, in the case of the monochord, by the length or the mass per unit length or the tension, but instead by the ratio of the frequencies of the notes, the frequencies of vibration. And by frequency of vibration, we mean the number of these pulses of the airwaves which strike your ear every second, right? So as this thing is vibrating, it's pushing the air, and the frequency with which this string vibrates dictates the frequency of the air pulses that are traveling through the air. That dictates the frequency of vibration of your eardrum, which then dictates the pitch which one hears. So the ratio of the frequencies is the main thing. And once again, the frequency can be affected by changing the length, changing mu, and changing the tension. But those are the, I guess, the the independent variables that affect the frequency that then affects the pitch. So let me stop there, and I will pick up this discussion in a bit more mathematical way next time.